Let us also resume commutative algebra. Let A be a ring and M and N both be A modules, that is, they are modules over the same ring A. And let me remind you of the fact that our rings are commutative and have identity element with respect to multiplication. Then a map F from M into N is called A linear or an A module homomorphism if the following conditions are true. For any two module elements x and y in M and any ring element A, f of x plus y equals f of x plus f of y. So f respects module addition and f also respects module product by ring elements. F of ax equals a times f of x. So from this definition we immediately see two things. This is the first observation. So F is a homomorphism between the abelian groups M and N. Any module is an abelian group with respect to its addition, and this first equation tells us that F is a homomorphism between these two abelian groups. Second observation, if A is a field, then the modules are just vector spaces over A. And then these conditions tell us that F is just a linear transformation from the vector space M into the vector space N. The set of all A module homomorphisms from M into N is denoted by this notation, hom suffix A M comma N, or simply by hom M comma N if it's understood what the ring A is. Do you see the similarity between this one and Herstein's notation, where we studied algebra of linear transformations? And just like algebra of linear transformations, here also you can turn this set into an algebraic structure by defining two operations. And we define addition and multiplication. Here I have just written multiplication, but I could have written scalar multiplication, since we do not normally call the ring elements scalars when we are studying modules, as we call them in vector spaces. So I just wrote multiplication here. Anyway, so these are the operations on hom M comma N. Let's see what they are. For any two F and G in this set, what does that mean? It means that both F and G are A linear functions from M into N. And a ring element A in A, we have defined F plus G and AF. This X of course comes from the domain module M of these functions F and G. F plus G of X means F of X plus G of X, and AF of X means A times F of X. So you see that this is how we also define similar operations in Herstein's algebra of linear transformations. Exactly similarly. The only difference is that there we had vector spaces, here we have modules. So you can expect what we can say about these operations, which is this. Then hom M comma N is itself an A module under these operations. And the proof of this fact is exactly similar to the similar fact you prove in algebra of linear transformations, which we have already seen in full detail. So I am not repeating that here. Essentially, you don't have to do anything. You just see, there we had vector spaces, which are basically abelian groups where the scalars come from fields. Here you have modules which are also abelian groups, but here the scalars come from a general commutative ring with identity element. That is the difference. All those verifications of the axioms, they are exactly the same. You verify yourself. Next, let M, N, M prime and N double prime. For some reason the authors have chosen double prime here, I don't know why. They could have called this one N prime, but anyway, this is how it's given in the book. So let these all be A modules. And then we say we have homomorphisms, A module homomorphisms, two of them. U is from M prime to M and V is from N to N double prime. Then these mappings induce further mappings. There are two, I have written one here, I will write the other one. This one is u bar, which maps home m comma n into home m prime comma n, and v bar from home m comma n into home m comma n double prime, defined by the following rules. U bar of f is f composition u and v bar of f is v composition f. Then this is what we can say about these functions, that both of them are A-linear, that is, they are A-module homomorphisms. Does that even make sense? Yes, it makes sense, because just like m, n, m prime, n double prime, these are A modules. So these home modules are also A modules, and that is why we can think of an A-linear map or an A-module homomorphism between these home modules. Okay, and these are such maps. To verify that these are A-linear, these maps, you have to go through some steps, of course. You have to first of all show that these functions u bar and v bar are well defined. What does that mean? It means that, say you take f, where will you take f from? F, of course, comes from the domain of u bar. Say you want to show that u bar is A-linear. So you choose f from here. What does that mean? F is basically, it means that f is a function from m into n. Then what is u bar of f? U bar of f is f composite u. What type of function is this? When you apply this function on something, first u gets applied and then f. So that means this will be a function from the domain of u to the codomain of f. Domain of u is what? M prime. And codomain of f will be what? Since f comes from here, and so f is a mapping from m into n, the codomain is n. So this is a function from m prime to n. So okay, you have got at least a function from m prime into n, right? But then you have to show that this function belongs to this home module. That involves showing that this function is also an A module homomorphism. Okay, and then it proceeds like that. So you do it yourself. There is no unusual twist or difficulty in it. It will be a bit lengthy. And next we have a remark. For any A module M, there is a natural isomorphism between these two modules. M is an A module and this is also an A module. You see A here, okay. A itself is an A module, so this makes sense. This one I am going to verify now. The authors have in fact suggested the function which gives us this isomorphism, and that function is this. So I give it a name, say I call it psi. Psi is the function from home A comma m into m, and the definition is this. Psi of f equals, by definition, f of 1. Let's see what it means. So the input f comes from this home module. That means f is a function from A into m. Basically it's the function from A into m. So the psi image of f by definition is f of 1. What is this f of 1 and what is 1? 1 is the identity element in A, the multiplicative identity. And because f is a function from A into m, f of 1 is a unique element in M. So that is why psi is well defined at least. And next we show that psi is itself an A module homomorphism. For that we choose two elements in the domain module, which is home A comma M. Those two elements are f and g, and a ring element A from the underlying ring. Now we have to verify those two conditions, that psi respects module addition and that multiplication by the ring element A. So first we see addition. Psi of f plus g by definition is f plus g of 1, which is equal to f of 1 plus g of 1. How? How is this step justified? This is justified by the definition of addition. What is this addition? This is the addition in the module home A comma M. that we defined today in fact. But then f of 1 is just psi of f and g of 1 is psi of g. So we see that yes, psi actually does respect addition, module addition. And then next comes multiplication by ring element A. So we take psi of AF, that by definition of psi is AF of 1, and this equals A times F of 1. Do you see the significance of this parenthesis here? This quantity means the AF image of 1, where AF itself is the function. But then by the definition of multiplication by ring elements in the home module, this itself means A times F of 1. Here we do not use the brackets anymore because now we treat f of 1 separately. Okay, it's an element of the module M which you are multiplying by the ring element A. So ultimately the product is again in M. But this f of 1 is just psi of f. So that's how psi also respects this multiplication. So this means that psi is a linear or an A module homomorphism. Fine, so we have found that psi is a structure preserving map between the modules home A, M and M. But that's not enough. We now need to show that psi is also bijective. It's one-to-one and onto. So we take two elements f and g in the domain of psi whose psi images are say equal. Now if we can show that then the elements f and g are themselves equal, then that would mean that psi is one-to-one. And this just means that f of 1 is equal to g of 1. Now how can you use this condition alone to show that the functions f and g are equal? This one only says that they are equal at the input 1, but does that imply that they are equal everywhere? So let's take any element b in A. A is the common domain of f and g, and say we consider f of b. Now of course in the ring A we can write b as b times 1. Then f of b times 1 is equal to b times f of 1. How? What is going on here? How are we treating the ring A? We are treating the ring A as also a module, because in that home A, M, A is one of the modules, M is the other module. And f is actually a function from the module A into the module M. Now when you treat A itself as an A module, module multiplication, that is multiplying an element of module by ring element, reduces to ordinary multiplication in the ring A. So in this product, this B you treat as coming from the underlying ring A, and this 1 you treat as a module element coming from the module A. After all, it's just A, but there is a slight difference in how we treat these things. And then what do we know about f? F is a linear. So f respects module multiplication. That's how B comes out. And we are left with f of 1. But f of 1 is equal to g of 1. And then you run these steps backwards with g. B times g of 1, because just like f, g is also a linear. So g respects module multiplication as well. So b times g of 1 is g of b times 1, which is equal to g of b. So you see that on the domain A, at every point B, f and g agree. So they are equal as functions. And that is why psi is 1-to-1. So that means we are now left to only show that psi is onto. So next we take any point M, any element M in the range or codomain, whatever you want to call it, M. Codomain of what? Codomain of the function psi. Now we need to show that this M is psi of something. But what is that something? That something has to come from home A, M. And that something is this. We define a function f from A into M. by this formula, this rule. Here this a of course come from a. F of a is by definition a times that m. Let's first see if this function even makes sense. For any ring element a from a, the output is a times m. What is this? This is the product of the module element m and that ring element a, which is your input. So where will this product lie? Again in M, and also for a given a, this will be a unique element in M. So at least this function f is well defined. But what about this remark? Then actually f belongs to a comma m. This part I am leaving to you. It's just a 2-line verification. You show that this f is an a module homomorphism from a into n. Okay, I am not again doing that, it's a routine thing. This f is in fact that element in this structure, which is what? The domain of psi, whose psi image will be n. Let's see how. This is how. Psi of f is by definition of psi f of 1, but then by the definition of f itself, f of 1 is 1m, and by one of the module axioms, the last one in fact, 1m is m itself. So that's how you have realized this arbitrary element small m as psi of something, and that makes psi onto as well. So psi is a module structure preserving map. It is one-to-one and onto between this module and this module. So that's why these two modules are isomorphic.